Welcome to the presentation on bridgeless isolated CPIC power factor corrected converter for electric vehicle battery charging application. In this study, the analysis, design of the bridgeless power factor corrected CPIC converter are emphasized concerning their applicability in electric vehicle battery charging system. Through the utilization of the cascaded controller, the analysis emphasizes observing efficiency gain and power factor correction in the closed-loop bridgeless isolated CPIC converter. The evaluation includes measuring the total harmonic distortion in the input current adhering to the guidelines set by the recommended IEC 6100032 standard. For every operating circumstances, the power factor of the input side is found to be equal to 1. This facilitate the superiority of the converter for battery charging applications. The scope of the project is significant reduction in conduction losses, reduced input ripple current, reduced size of the inductor, high efficiency of the converter, dynamic response of the converter is very fast, high power density. It can be used as a power factor corrected circuit for electric vehicle battery charger, and it can be used for battery energy storage systems. Another application of this converter is high power and high voltage applications, and also you can use this for renewable energy applications. This is the converter model. Figure 1 shows the conventional CPIC power factor corrected converter. It consists of an input diode bridge rectifier. Second one is the conventional bridgeless CPIC power factor corrected converter. We can eliminate the input diode bridge rectifier in the second figure. Third figure is the bridgeless isolated CPIC power factor corrected converter. In figure 2 converter, it is a non-isolated converter, but in figure 3 our bridgeless isolated CPIC converter is a isolated converter, that is a isolation between input side and output side using the transformer. Due to the absence of the dielectric rectifier at the input side, the bridgeless configuration presents superior performance by reducing input current, total harmonic distortion, enhancing power factor, and minimizing losses caused by additional rectification diode, resulting in an overall increase in efficiency. The high switching frequency operation of the proposed converter also reduces the size of the isolation transformer to achieve high power density. The circuit of the bridgeless isolated power factor corrected circuit is shown in figure. The circuit contains two CPIC converters which operate with no dependence on each other. One operates during the positive half cycle of the input AC supply, and the other operates during the negative half cycle of the input AC supply. Here we are going to design the power factor corrected based electric vehicle battery charger using a bridgeless isolated CPIC converter. And the main goal of this converter design is to reduce the input ripple current and to maintain high efficiency and to provide high dynamic response to the system. These are the design specification. Input supply voltage is set to 220 volt. DC link voltage is 18 to 12 to 82 volt. Power rating is 1.2 kilowatt. Line frequency 50 Hz. Switching frequency is set as 20 kilohertz. According to this design parameter, we are calculating the values of inductors and capacitors using the design equations. The input inductor value is given as Vs into D divided by 2 into Fs into delta into ILI. Li is the input inductance, Vs is the source voltage, D is the duty ratio, and Fs is the switching frequency. Delta IL is the ripple current in the ripple factor in the input inductor current. It is set as a 20% of the input current. And the value of the inductance to keep the operation of magnetizing inductor in discontinuous mode of conduction is calculated by considering the battery emulated resistance, which is equal to 5.6 ohm. By using LM12 equation, we can find out the value of magnetizing inductance. We are selecting the value of the magnetizing inductance is equal to 100 microhenry. In the capacitor Ci1 and Ci2, we can calculate using this equation N2 by N1 into VDC into D divided by delta VCI12 Fs into RDC, where delta VCI12 is the ripple capacitor voltage, which is equal to 20% of the input voltage across the capacitor. 20% of voltage across capacitor gives the delta VCI into delta VCI12. Then DC link capacitor value is also calculated. Then the designed values are input inductance Li is equal to 2 millihenry, magnetizing inductance is equal to 100 millihenry, capacitance value Ci1, Ci2 equal to 5.6 millifarad, and output DC link capacitor CDC equal to 2.8 millifarad, and transformation ratio of the transformer is taken as 1. The control of bridgeless isolated CP converter. The control of bridgeless isolated CP converter involves the generation of pulses for the two semiconductor switches. Switch S1 switches during the positive half cycle of input supply, and switch S2 switches during the negative half cycle of input supply. So the pulses that would be given to these switches will be generated from the same controller and can be given to switch S1 during the positive half cycle and to switch S2 during the negative half cycle. The control figure 5 shows the control diagram of bridgeless isolated CP power factor corrected converter. This is the voltage controller and current controller and PWM generator block diagram of the power factor corrected isolated bridgeless CP converter. To fully charge the battery, the cascaded control system seen in this figure is employed. It comprises of an outer voltage control loop and an inner current control loop that work together to maintain a constant voltage. This is the controller design equation. The voltage controller tracks a constant reference battery voltage VB star in a strict fashion to limit the error VBE with initiating a control signal VBB. At any random sampling instant K, the voltage error and control signal to minimize this error are represented as equation number 1. The controller voltage output VBB from the proportional integral controller generates the desired reference IB star for controlling battery current through the inner loop PA controller. This reference signal is compared with the battery current IB, and the error IBE is minimized using control signal actuated by the current proportional integral controller limit. The optimum accurating signal IBB for maintaining charging current is defined as equation 3 and 4. This is the MATLAB Simulink model of closed loop simulation of bridgeless isolated CP converter. This is the result of the bridgeless isolated CP converter. Here the supply voltage is 220 volt 50 Hz. For 0 to 0.5 second VDC reference is 60 volt for 0.5 to 1 second VDC reference is 80 volt. The transient performance of the isolated bridgeless CP power factor corrected converter for upward variation in input supply is shown in figure. The input supply voltage is simulation results for a sudden drop in supply voltage from 220 volt to 200 volt are shown in this figure. The waveform of supply voltage, supply current, switch voltage and currents, output DC link voltage and output current. The waveform clearly illustrates that the supply current exhibits a sudden rise without compromising its sinusoidal nature regardless of the decrease in input supply voltage. Simulation results for sudden rise in supply voltage from 180 volt to 220 volt is shown in figure. The waveform of input supply voltage, input supply current, switch voltage and currents, output DC link voltage and output current. By analyzing the waveform, it becomes evident that despite a sharp increase in the supply voltage, the supply current experiences by sudden decrease while still maintaining its sinusoidal feature. The response of the isolated bridgeless converter is also examined for an abrupt change in reference output DC link voltage from 60 volt to 80 volt. It is observed that the value of the input supply current is varied to keep the DC link voltage constant. The power factor is seen to be unity with the input supply current THD remaining within the acceptable limit. This THD in this figure is shown as THD is 2.82. The performance comparison of the bridgeless epi converter with a conventional dielectric rectifier based and traditional converter based charger is shown in figure. Again, this improved input current is improved and THD is reduced when we compared it with a conventional SIPI converter. Power factor is also improved. The central theme of this project revolves around designing and evaluating a bridgeless isolated SIPI power factor corrected converter for battery charging application. It thoroughly describes the circuitry, mode of operation of converter, design formulas, and control strategy for discontinuous conduction mode. Through the simulation in MATLAB, simulating the performance of converter is analyzed for various operating conditions. The evaluation includes measuring the total harmonic distortion in the input supply current adhering to the guidelines set by the recommended IEC standard. The input side power factor is observed to be unity for all the operating conditions. This substantiates the superiority of the converter for battery charging applications. These are the important references. Thank you.